we need to have tools that are much more sort of engaging, so that we can actually be critical about what we're doing. And that is what, at least we believe, the chemometric tools can do, is that they can actually allow you to be critical about the data scientist. Instead of you being afraid of the statistician and not daring to say anything against what that person is saying, we need tools where anyone can complain and say, hey, that's not right and that's not good. The operator in the production, the doctor, the technician, all of them should be allowed to chip in on the data analysis. And that is what we can do with many of the tools that we have. So for example, if we look at PCA, here's a simple visualization of what we can do with PCA. So here's a table. It's a silly little table with just 3 variables. And every person has a measurement on each of these 3 variables. So we can put those on 3 axes, and we can actually turn that into a coordinate system. And now Smith here becomes a point in this coordinate system. And we haven't really done anything. We've just plotted Smith's measurement in this coordinate system. And you can still read them because you know how to read the axes on a coordinate system. But if I plug in all the samples in this 3-dimensional coordinate system, then what we're going to see is that it turns out that in this particular case, these 5 samples, these 5 persons, they don't really fill out the whole 5-dimensional coordinate system. They're kind of lying on a plane, not exactly, but they're kind of lying on a plane. And I can actually put a plane in there in such a way that all the points are close to it. Now, if I do that, I can also measure how close each point is to this coordinate system. And the way I put this coordinate system is that I do it in such a way that all the distances are as small as possible. And mathematically, that's in a least square sense, but that's not super critical to know. So still, I haven't actually done anything. I'm just playing around with the data, and I added this window here. Now, what I'm going to do now is that I'm actually going to remove the original data. So remember the orientation of the 3 axes, the blue, the green, and the red one, because now I'm going to project everything into the plane and remove the original axis. So now I did something. And what I did is actually I did a 2-component PCA model. And the point I want to make here is that we get a very nice visualization where I can actually still get most of the information from the original data table, but I can do it in such a way that I am comprehensively understanding everything that's going on. So for example, we can see that Johnson is pointing in the upper direction. And since the green axis was in the upper direction, Johnson must have high values on the green variable. And Jones, in the same sense, must then have high negative values. I can also see that I don't know much about the blue variable, and that could be either because it is not related to the green and red one, or it could be because it's not showing much variation. And all of this is kind of nice, and it's actually nice to the extent that the model is nice. So that to the extent that we are describing our data well, this is a nice visualization. And what is really nice about this, and that I'm sure you're familiar with, is that you can explain this to anyone. You can explain score plot and loading plots and stuff like that. And that means people can start arguing and saying, I don't understand why these samples are close or why these variables are correlated, etc. That's a huge benefit from the more classical univariate approaches. But multivariate models are by no means simpler in themselves. I mean, if I only have one variable to look at and understand, that is simpler than having 200 per definition. So actually, the sort of the number of mistakes or the risk of being blinded by certain things is higher when we have multivariate data. So we still have to know even more so what we're doing and how we're doing things. And let me give you some examples of considerations. First of all, with all these multivariate tools that we have, one of the most powerful aspects of them is that we can visualize our data. So in a PCA model, we can visualize our scores and our loadings. And here we have a score plot of some samples. It's not important what they are. But just the score plot in itself is nice. We can look for groupings, etc. But what we can also do is that we can color by different things. Here I colored by replicates, which actually doesn't seem to be too nice here. But if I do just a small little trick and I connect replicates with a line like this, well, if I do that, suddenly we see that even this visualization is actually quite illustrative, and we see that there are some problems. Most of the replicates are extremely close to each other, but then a few of them are actually quite far away from each other, indicating some kind of problem. And we have tools that we can then use to understand what this problem is. In this particular case, it's related to some scattering in some near-infrared spectra, but that's not the point I wanted to make here. But the point I'm trying to make is just that sort of being a little bit adventurous with your coloring, you can actually you can actually include all the meta information you have in your data. You can plot color by discrete classes, like these are the Greek samples and these are the Spanish ones, or you can color in a graded way if you have some numerical values. Like here, I have colored a score plot by specific X variables, for example. It could also be by temperature or by measurement order, stuff like that. So lots of different things that you can do, and the more creative you are with including your metadata, the more you can learn from these models. Talking about scores and samples, one important thing is what sample you should use in a model. And there's sometimes this misunderstanding that you have to use design of experiments when you build models. Now, I would like to at least add some details to that. And I'm going to use maybe some slightly silly examples. But anyway, if you're doing MSPC, and I don't know if you're familiar with MSPC, but that's multivariate statistical process control. So let me give you an example. Let's say I have a production, I'm producing milk, and I don't know how a process upset will look, but I do know what a normal operating condition is. So I take a lot of measurements in my production during normal operating conditions, which is what we call NOC, normal operating conditions. And I build a PCA model. That's basically how you do multivariate statistical process control. I mean, you could talk for days on that alone, but that's the simple idea. I make a PCA model of normally operating samples. If I take a new sample and it's an outlier, well, if I take a new sample and it's not an outlier, that means we're still in normal operating conditions. But if I take a sample and now suddenly it's an outlier, it means something is wrong. We are no longer in normal operating conditions. And then you have to stop the process and use the tools that we have, like contribution plots and stuff, to investigate what's wrong with the production. But what's important here is that you definitely do not want to use design of experiments to build such a model. You really need normal samples. And that actually specifically means boring samples. To the extent that if you have an extremely nice production where the process is very much in control, what's the variation going to be in such a production where everything is well in control? It's actually going to be close to nothing. It's going to be just random noise. That's like that's like the perfect production where you have controlled your product to the extent that you only have small random variation. So actually, in a very nice MSPC model, you may describe 10% of the variance in the data. If you're describing 99% of the variance in your data in an MSPC model, that means you have a lousy production where nothing is in control because you have systematic variation. In a good production, you want only small random variation. But here, the point I wanted to make is that you definitely do not want to design anything here. You just need to go out and grab the empirical samples that are there. So to give you an analogy, which is really stupid, I apologize, but just to make it a little bit more simple, if I want a model that checks if a rat is normal size, I don't want to use all kinds of animals in that model. I want to use just standard normal rats. I know it's a stupid example, but I hope you get the idea. Okay, so this is an example where we definitely don't want design of experiments. But then we can take another example. If I have the task to build a regression model that predicts whatever protein content as nicely as possible, then definitely I would like to use DOE. And when I say DOE, I'm actually not even, I mean, it's not so critical that your samples come from a design of experiment, but what is really important is that your samples are spanning the variation. So you have samples that span all the types of variations that you would like to see in the future. And DOE would just be one way of doing it, but it's definitely not, in many cases, it's not critical that it is indeed DOE. The critical thing is you do want to go to the extremes in order to be able to span whatever variation you see in the future. And if I should give you a similarly stupid example here, if I want a model that predicts the size of new animals, well, then, of course, I shouldn't just use rats of normal size. I have to use all kinds of animals to be able to do that. And yes, I know the example is still silly, but I hope you get the point. You actually have to know what's the purpose of the model before you can decide how do I sample well for a given model. It's not something that is given beforehand. It depends on what you have specified is the purpose of this particular model. And from that, you will know how to best sample your model. Okay, another problem I would like to mention, something that is sometimes a problem, especially nowadays. In the good old days, which were maybe not so good, but in those days, you would measure variables that were relevant for you. I mean, you would measure the pH because you knew the pH was important for your fermentation or whatever. Nowadays, that's not what people do. Oftentimes, you just go and push the button of an instrument and you get all kinds of data. You get 2,000 variables, not because they're relevant to you, but because they came out of the instrument. And that actually profoundly changes how to deal with your data, because now you don't have relevant data. You have just the data that came out of your instrument. And hopefully some of it is relevant, but oftentimes it's not all of it. And even sometimes it's not even most of it. Well, here's an example of some spectral data of beer samples. And if I do a PCA on these, I find some outliers. But actually, in this particular case, the purpose of this modeling was to predict a certain quality of the beer, the sugar content mainly, but never mind that. Now, that information is mainly present here. If I build a PCA model of that part of the data, I find completely different outliers. These ones are not outliers anymore. These ones are outliers because they have an extreme color, but that's not of any interest for me because I'm not trying to model the color of the beer samples. I'm trying to model the sugar content, and that's a completely different thing. So outliers depends on what data you have, and it's kind of a rookie mistake to just take all your data and start looking for outliers in that. But maybe you should first look into the relevance of your data. And in reality, you should maybe combine these things. But anyway, the important point here just to make is that when your data is not specifically relevant for your problem, you have to be a little bit more considerate than in the good old days. I'd like to mention also a little bit about how to interpret loadings or how not to interpret loadings. Now, here's a loading plot. It's 10 different variables measured of sugar samples in a sugar factory. Not important for the points, but for the points I want to make. But I would like to mention a little bit about what we can interpret. So for example, I can see that ash and SO2 are correlated because they're close to each other. But, and this is important, they're correlated with respect to the 60% that we're seeing here. So I do not expect them to be perfectly correlated at all. If these two components were explaining 99% of the variance, then I would expect them to be almost perfectly correlated. But here, I specifically don't expect that because I'm only explaining 60%. So what is a nice, useful thing for you, at least mentally, is every time you claim something from a loading plot or a score plot, you end it off by saying, with respect to these 60%. Because imagine you're looking at components 7 and 8, which are explaining 4% of the data. It has no repercussion for the raw data. So being close like this in components 7 and 8 means nothing with respect to how these data are correlated in the raw data. So keep that in mind when you're interpreting. And also keep in mind that being close is not necessarily significant if you're lying close to 0.0, especially if your data is auto-scale. Then we don't really know much about these. So be careful about over-interpreting these things. Now, there's a nice trick that you can use, because whatever you want to say, if you want to say ash and SO2 are correlated, well, you can so easily verify it. Just plot them against each other, and you will see, and you will become smarter and learn what does it actually mean. And that goes for many of the things that you sort of try to conclude from your data. You can often verify it by just digging a little into your data. So this is over-interpreting. There's also sometimes a risk of under-interpreting. I've seen too many scientific papers where people spend a lot of time trying to figure out how many components there are, but then they only discuss component 1 and 2. And I mean, there's nothing wrong in only discussing 1 and 2. They're typically the most important ones because they're big. But if you don't want to look at more than 1 and 2, you can skip this part. I don't care how many components there are if it has no effect on your analysis. If your whole analysis is based on looking at component 1 and 2, that's perfectly fine with me. But then I really don't need to know that there's 7 components in your model. Only if you use that thing for something. Let's talk a little bit about how to handle outliers in models. First of all, initially when you start learning to do data analysis, you would so much like to follow a protocol because that makes life a lot easier. So you would like to first check for outliers, then determine the number of components, then do variable selection, then select pre-processing or whatever. And the fact is that simply doesn't work. The reality is you have to do everything simultaneously, and that hurts initially when you're new to data analysis. But in the end, it actually ends out being not such a big problem. You get used to that you have to handle everything simultaneously. You kind of have to hone your way into a nice model. So what that means is that if I removed 5 outliers, then definitely I have to reconsider what the number of components are. Or also the opposite. If I significantly change the number of components, I probably have to look at the outliers again. Also, when we talk about outliers, remember that an outlier is not a sample lying furthest apart. There's always going to be a sample like this. That doesn't make you an outlier. What makes you an outlier is that you're very far away from the other ones. That's an outlier. And also related to that, remember that an outlier is not a wrong sample. An outlier is just a sample that's different from the other ones. And sometimes the reason for that is your fault. Maybe you sampled in a stupid way. Maybe you wanted samples that were red, green, and blue, but you only took blue samples and 1 red one. So naturally, the red sample comes out as an outlier. But the conclusion that you would reach is that, hey, I need to sample better. So it's very fine to identify outliers. We have a number of tools for doing that. But once you have identified, once you have identified the outliers, don't remove them, explain them. And this is such an important trick. Once you explain the outlier, then you will know what to do. And when I say explain, it's not saying, hey, the Hoteling's t-squared was 5 times higher than all the other ones. No, it means going back to the domain knowledge. Sample 5 had a high Hoteling's t-squared, and looking at the loadings and the contribution plot, we see that it's because it has much higher humidity, and that's a problem because blah, blah, blah. And from that domain insight, there you're going to find the solution to what do you want to do with the outliers. So don't remove outliers just because you don't like them. Imagine, let me make an example. Imagine that I'm trying to build a linear regression model, univariate. This is going to be a lousy one, but now I'm going to remove some outliers. And now I actually have a nice model. I hope you can see that that's probably not the right thing to do. And the reason being, you cannot remove outliers just because they are far away. But if I can explain that all these samples are wrong and these samples are wrong, then I have to remove them. And that's why you have to explain them. Always explain. So it's always on you, not on the statistician, so to speak. In relation to outliers, in many types of software, we have these confidence limits on different things, on the Hoteling's t-squared, on the leverages, on the residual variance, etc. They kind of deceive you into sort of thinking that everything outside the confidence limits are outliers that should be potentially removed. It's a very good idea to just remove these confidence limits, to not let yourself be fooled by them, unless you have some very statistical reasons for using them. Okay, now I want to talk about some really important aspects of building regression models and multivariate calibration models like PLS models or neural network models, these kind of things. So it's related to how you can misuse correlations and regression coefficients and things like that. And I'm going to show you several ways that they can be misleading, and hopefully it'll make sense to you. So here I have just a univariate linear regression, a model that predicts 99% variance. You can see that we have an outlier. If I remove the outlier, then I get 70% variance described. So when I remove the outlier, the variance explained is reduced. Now let me take a completely different example. So this is another example. Here I have an outlier and the variance explained is only 40%. If I remove that outlier, then I get 93. So in the upper example here, the variance went down, and here the variance went up. So my question now is that in the upper case, which of the models is better? Is it this one or this one? And in the lower case, is it C or is it D? And you can think a little bit about that. Now, in order to see which one is better, we have to actually look at how well do they predict. So we have to look at the error of these things. This is the error in my prediction. And here the average error is 0.3, well, 36, and here it was 0.5. So actually this is better than the left model. And down here, it's actually the same thing. The right model is better than the left model. And the point I want to make here is that the variance explained has nothing to do with whether we improved or not. So in one, the variance goes up, and the other, it goes down. And I hope it shows you that you cannot use variances. Oh, ooh, we have someone talking. Do we have a question, or someone didn't turn on the mic?
Anyone wants to speak, or just mute the mic, please?
That's fine. I can mute people like this. Okay. Anyway, so I hope you can see that the variance explained does not tell me whether a model has improved. So imagine you're doing outlier detection and now you argue, hey, my variance is now 10% better, so that's good. I will claim that that's nonsense because it can go up and down whether your model improves or not. Let me give you another example. Let's say I'm doing linear regression again. Let's say that these are my data. I think you can see that the correlation is going to be 0 here. The variance explained is going to be 0. Now I add a point up here, and boom, now my variance is going to be 0.99 or something. But it's still the same lousy model down here. The problem is where the variance explained, you know, let me try and the 99 is in terms of this span. The 70% over here is in terms of this span, and you cannot compare percentages of different things. It's like apple and pears; they're not comparable. So it really simply doesn't make any sense at all. You can't use these for arguing in your modeling. Oh, now I do this because the variance goes up. What you can use them for is when you're done and you have a model and you go to your boss and you can say, hey, look, boss, I have a nice model. It explains 95% of the variation. That's fine. And they like 95% or 99%. So that's good. But you can't actually use it for optimizing your model and making choices. That's really important that you sort of see or get the gist of that. And not only are correlations annoying or variances explained annoying in that sense, we also have a number of different types of correlations. We can have indirect correlations, we can have spurious correlations, confounding, etc. And let me give you some examples. This is some data that we were working on many years ago, like 12 years ago or so. We were looking into cancer, ovarian cancer with mass spectrometry. Now, we took samples over an extended period and kept them in a freezer. When we measured the spectra, it turns out that we could actually predict how long the samples had been in the freezer, which is not in itself a huge problem, except all the sick samples were taken in early and the healthy samples late. And that means I could get perfect predictions of whether you had cancer with these data because I had stored the samples in the freezer for a long time. So it was nonsense results because of some indirect correlations that I had induced due to the way I sampled. Now here we saw it and realized it, and that's fine. So we could correct for it, actually, what we did was we corrected for it. But in many cases, you don't really know about these things, and then it's just going to be, you know, sometimes you see a result and you think it's real, but it's actually nonsense. I remember a famous case a long time ago when the gene expression was sort of in its infancy, and there was a company created that they claimed they could detect cancer. But all the healthy people were from US and the cancer people were from Norway. And really what they were seeing was the nationality and nothing else. And there are tons of those examples. Just be very careful about confounding. Now, regression coefficients is something different. A regression coefficient is not directly related to a correlation at all. I want to talk about regression vectors because ultimately we tend to use them quite a lot for interpreting. And if you think about a lot of clinical research or epidemiological research, I mean, that's the regression vectors that people are looking at when they say wine is healthy or cheese is healthy or is not healthy, etc. Then they're really looking at regression coefficients. So they are important. Now, let me explain regression vectors in a spectral setting. I'm assuming that all of you knows a little bit about spectroscopy and Beer's law. So let's say this is my analyte of interest, but in the samples I measure, I also have this interfering signal. So if I have a calibration set, it's going to be with different variations of these ones. So yeah, that's a bad drawing. But anyway, the regression vector, if I build a PLS model or something like that, is going to look like this. It's going to have the same shape as my analyte. And you can sort of understand that this would work if I take a sample like this and take the inner product with the regression vector. That's how I predict. It's not going to see any of the interfering signal. But if my analyte doubles, I'm going to get twice as high a prediction. So it makes perfect sense. And here, this regression vector is very much is very easy to interpret. But now let me make it just slightly more complicated. Let's say that the interfering green signal is overlapping with the blue one. What you're going to find is that the regression vector is going to change. And mathematically, what it is now is that it's actually the blue one orthogonalized with the red one. I don't know if you can see for yourself, but if we have, I can only plot two wavelengths here, but this is wavelength 1 and this is wavelength 2. Now maybe this is the blue analyte and this is the green one. In reality, it would be in a 100-dimensional space. Now they are correlated. So what I'm going to do is, this is my analyte, oops, and this is my interfering. What I'm going to do is that I'm going to look now in this orthogonalized direction, because now I'm blind to the interference, but I'm still seeing if the signal doubles here, I'm going to see that in my orthogonalized signal. I know that's a little mathematical, but that's the reason why this one becomes the blue line orthogonalized with the green line. That means I'm blind to green stuff. I don't see that interfering signal anymore, but I still perfectly see my blue signal. What is really interesting here is that now I need part of the spectrum where there's no blue analyte. So I'm going to have regression coefficients that are non-zero for real, where there's no analyte, because I'm correcting for the green one. Even worse, look at this. I'm going to have a negative regression coefficient, even though the actual effect is positive here, but that's because I'm correcting. So you see, I can actually have positive, negative, or zero regression coefficient, even though all three variables are positively correlated to my interfering signal. So what I could say here is that if in some sense this was related to, let's say, smoking, then maybe we would incorrectly identify smoking as healthy because we didn't see that this particular variable was just correcting for something else. And you have to remember that this is a kind of a stupidly simple example. In reality, life is much more complicated. So the point here is that regression coefficients can be positive, negative, or zero, no matter what the reality is. No matter if there is an effect of the analyte, and no matter what the effect of the analyte is. And that will happen in real data. So that's regression coefficients. Now let me actually just take us back to correlations and see what they would do in some kind of spectral data set. So let's say I have my analyte of interest, that's the blue one, and I have an overlapping signal. Now I generate a data set with different concentrations of blue and red, and these concentrations are unrelated to each other. If now I check at every wavelength, what's the correlation to my blue? I will see that in the latter part here, there's a high correlation, and in the left part, there's zero correlation because this is going up and down without being affected by the blue. The blue part is not 1, because the red interfering signal is also active there. This kind of makes sense, but what happens if the analyte and the interfering signals are going up and down together? Then I get a positive correlation, even where I have no signal, no analyte. And if these two compounds are negatively correlated, I can get a negative correlation. Okay, so maybe you don't get all the math here, but before I showed you that regression coefficients can be whatever. And what I'm showing you here is that the same holds for the correlations in the raw data, because we always have biological correlations between different chemicals. And therefore, we can see any kind of correlation. And in these three cases, the regression coefficients, the regression vector would have been exactly the same. I'm not going to go into the detail here, but the regression vector would be exactly the same. So the point, if we boil it down and forget all the examples, is that regression coefficients can be whatever, no matter what the real causal sign is, and exactly the same for correlations. And they can be that sort of irrespective of each other. So really, you have to be extremely careful when you interpret models, because you have a tendency when you start looking into these models to overinterpret and add causality. You really have to be careful with doing that. You may hypothesize, and that's perfectly fine. You may say, oh, my loading plot is like this, so I think that fruits will cause cancer. But then you have to go and verify it somewhere. It's perfectly fine to get the idea, but you really, really have to be careful. There's no causality in the models that we use here. Okay, I hope you get at least the concluding part of this. That's the most important. Now, here's another important point I would like to make. Here, I'm showing you two different predictions from completely different models. So this is, the left one is predictions of protein based on NIR. And on the right side, something called falling number. That's something in flour research when we make flour from grains. And the question is whether these two models, each of them, are good or bad. And the actual point I want to make is that this may actually be a perfect model, and this may be a lousy model. And so allow me to give an example on this. And I think the easiest thing is to show, let me go to MATLAB and show you an example. Let's see, let's do this. Okay, so I'm gonna do this. So what I'm gonna do is that, and never mind all the code here. So what we have here is that I generated 1,000 points, and I made a true value of some reference that is exactly correlated to my X. So let me plot these. We need the plot here. Okay, now in reality, we never know the truth. You send your samples to Eurofins and have them determine the growth hormone, the fatty acid, or whatever. They don't give you the truth. They give you something which has noise. So what I'm going to do now is that I'm going to add noise to my data. I'm going to add of a magnitude of 0.4. So now if I plot my real Y, the other one I don't actually know, this is what I have. And now I want to build a model. And let me actually build I'm just going to use PLS. But since there's only one Y variable, it's basically just an MLR model. I'm using something called PLS Toolbox, which is not important for the example. My real one. Okay, so if I build a one-component model and I look at the predictions, let's take a look here. Here we are. They don't look too impressive, right? But remember that I have an error on my Y variable. So let me actually, this time I actually have the truth. So I can apply this model that I developed here to the true data. which we don't normally have. I mean, we never have that, but because I simulated the data, I can actually do that. So let me actually apply this model that I made, which looks pretty sad, but let me apply that to my actual true data. So I'm not using the true data for calculating the model. And let's take a look at the predictions. Here you are. So these are the predictions, which is pretty impressive. Now, what's happening here is that normally when you look at your model and you look at the error it gets, you kind of take the blame for that. But this number here is not the error of the PLS model. It's the error of the PLS model and Eurofins, meaning your reference. So it's not, and this is extremely important, this is not just the error of your model. Let me actually make the equation. Let me see if I can get this one up here. So normally you would take full blame for the error, but what it really is, is that it's the error of your model and the reference. And I already knew, because I made the data, that I had an error of 0.4, and I see that my RMSECD is 0.4. So what does that mean? It means my model is perfect. Now, this is extremely important. I don't think I can exaggerate how often I have seen people spending months trying to improve something that's already perfect. And the only way you can know if it's perfect is if you have a really good estimate of the reference error, because this error here is not the error of your model. It's the error of your model and the reference. And most people just ignore the reference. And that means you take all the blame. And that's just such a bad idea. It's a really, really bad idea. So this may be the single most important point I have to make, that without understanding the reference error, you have no idea when you're actually done with your modeling. Okay, let me actually maybe skip beyond the cross-validation and move on to how you can cheat yourself with overfitting. And I'm going to give you an example. Well, here's an example from literature. This is an example of something called electronic tongue, which are notoriously silly instruments, most of them, not all of them, but most of them, with drifts in the sensors and stuff like that. They really work bad. This particular one has 7 sensors. And in this particular case, the guys were trying to predict the bitterness of 7 different chemical compounds, which is a difficult task, especially with the kind of sensors you have in an electronic tongue. But regardless, they get almost perfect predictions. Now, I tried to get the data from these authors, but they wouldn't let me have it. But it is beyond any doubt that this is calibrated data, not validated. And so they obviously have no idea how to use PLS models in a proper way. 7 samples, 7 sensors, and perfect predictions, which with an instrument that is typically haunted by drifts, that is absolutely impossible. I'm going to give you an example of how we can do some similar kind of cheating. Let me open. Oops. Let me make a data set in MATLAB. Where's my mouse? Here. So I'm going to make a data set, absolutely random data, as an example of a metabolic data set, for example, if you're doing metabolomics. So I have 100 persons, say, and I measured 200 metabolites. And then I randomly assign half of them as sick and half of them as healthy, something like that. And now let me do a PCA model. So it's basically random data. So I don't actually expect to see any kind of grouping in my data. Here you see a score plot. And let me just take score 1 versus score 2. Okay, that all makes sense, and that's good and fine. But now, what is often happening in metabolomics is that people will start out doing a PCA and see if they find a grouping, but then maybe they get a little bit desperate, and then they say, okay, but then let me do a PLSDA on the data. Oops. Here we are. And see if I can actually find a classification model that can distinguish between my sick and healthy people. So let me get this one over here. And let me, hey, wait a minute. I think I actually forgot to, no, I did not. Okay, that's fine. And sorry. Here we are. So let me do score 1 versus score 2. Look at this. I have a perfect separation. And of course, that's meaningless. There cannot be a perfect separation because it's random data. If you go through sort of, especially in metabolomic literature, you will find these kind of examples. A little bit similar to the p-values I started out mentioning. These people will also give you the R squared and Q squared. That will actually show you that this is nonsense. But people will come up with all kinds of claims like, well, I'm not interested in really classifying, I'm just visualizing my data. But because this model actually doesn't validate, that specifically means you can't look at it. When it doesn't validate, when the classification is 0 or whatever, that specifically means that whatever is showing is nonsense. This is absolutely meaningless. You can also see the variances described are extremely small because it has to look at really weird stuff to find any kind of separation. And as soon as you validate this, you will see that it's absolutely nonsense. Okay, almost done. Whoops, sorry. I want to mention a little bit about the principle GIGO, garbage in, garbage out. One thing that people often neglect is to spend time on actually doing quality assurance of your data. And it all starts with your data. So understanding the quality of your data is number one. Here's some examples from investigations we did where we initially tried to build PCA and PLS models, and it didn't work well. And only after that, we went back and studied the raw data. And suddenly we saw things like this, a drift in the data suddenly. And we found out that it was related to a change of technician. Also, we saw something like this, which is no limit of detection, which, well, I have many opinions about, but that you really shouldn't have in this kind of investigations. Now, understanding the quality of the data, really understanding is extremely important. We have a tendency to trust data that come from fancy laboratories, but these are human beings and they make mistakes and they're not used to the setting you're in. So you have to look into the quality of the data. Sometimes people believe that we can correct for artifacts, and we can sometimes, but it always removes signal from our data. So it always gives us lower quality data every time that we handle artifacts. And sometimes we may lose essential information. Now, the last thing I want to talk about is causality versus correlation. If you look at the sales of sunglasses, that's correlated to the sales of ice cream. That's a real relation. It's indirect, but it's a real relation. And you know, I can predict how many sunglasses are sold from the sales of ice cream. I only need correlations in order to be able to predict. Now, causal relations are direct relations. If I add more analyte, I get more absorbance. That's again, it's a correlation just like above, but now it's causal, and I can actually affect, the absorbance. If I want more absorbance, I can add more analyte. Now, with a causal relation, I can optimize and I can fundamentally understand. With a correlation, I can predict. And people will often tell you one or the other that, oh, you cannot predict if it's not causal. Absolutely untrue. I can predict with any correlation. I just have to be careful when it's indirect, but I can still predict. Let me show you some examples, and you know these ones. This one says that drinks will increase the risk of cancer. Now, the reason you know it's not true is that it says here that it's a study of 1 million women, and they didn't go out and told 500,000 women to drink heavily and told the other 500,000 people not to drink. So it's not a design, it's just a random, it's a correlation, it's an empirical correlation. And it might be anything that's correlated to wine consumption, and there will be a lot that's correlated to wine consumption. The really sad thing is that 10 years later, someone else is going to do the same study and find the same correlation and say that it confirms the old paper, which it doesn't, because it's still only a correlation. It's fine to get the idea from a correlation, but it doesn't prove anything. And even scientists struggle so much with that. Here's an obvious wrong thing. Chocolate may help people get slim, or chocolate can predict how many Nobel Prizes we're getting, which is pretty funky. And I don't know, maybe it's economical development or something like that, but it's definitely not the chocolate. Now, I'm almost done. I would like to just mention these ones. I'm going to get you the slides afterwards so you can take a look. This guy here, actually, you may just Google his name. He has a wonderful story about how he started reviewing a paper and ended up spending years that led to several doctors being fired at a university, and a clinical trial was stopped before they were actually going to do the opposite of what was meaningful, etc. It's kind of like all the mistakes that we all do, but these guys, they did all of them at the same time. And this guy did the CSI work to figure out what it was. Last slide, I promise. So this is a recipe for how to get really bad results, and it's going to be useful in the end. But anyway, so if you want useless results, you should measure a lot of unknown stuff and call them semi-quantitative. That basically just means that it's a bad measurement. Make sure they're all correlated, so anything can pop out instead of other things. So your biomarkers are going to be pretty much random, and take very few samples. That's the way you can generate really, really bad results. And if you look at it, it also gives you the recipe for getting good results. And where this all really starts is by being insightful and knowing what you're doing. And with that, thank you very much. I hope that it was useful.
Oh, thank you very much, Rasmus.
Thank you.
So I don't know if there are questions in the chat. Yes, there is a question. Rasmus, can you read it?
Yeah, I will read it. So the question is, in the story about predicting perfectly and like that, could it happen that the PLS error and the reference error go in opposite ways, so they kind of cancel out, and the apparent error is lower than the reference method? Yes and no. So let me just bring up this thing again. So what I said is that the error we see is the PLS error plus the reference error. And it's a squared thing because it's variances. So ideally, they cannot cancel because they're positive numbers. So there's no way they can cancel each other. Now, in reality, all these numbers here are estimated. So of course there can be obscure situations, like if this one is 9 and this one is 4, then it doesn't add up anymore, because we forget that there is an uncertainty on these numbers. But ideally, if you have good estimates of these, they cannot cancel each other. Well, they can never cancel each other, but there can be, you have to remember that these are only estimates.
Okay, there are more questions there. Even here, there is a question here in come here. Yeah.
Hello, Professor. That's nice.
Closer and louder.
Okay, so I have a question regarding the electronic time presentation that you made. So there is a error that they didn't consider the LOD, the limit of detection. Do you think that can be a, let's say if you estimate the LOD and then plot the model, do you think that will be a solution?
Well, I'm so sorry, but I think the sound didn't come through well. Can you
Closer. Shout.
Professor, the limit of detection for the electronic tongue sensors, do you think that could be a problem solution for the problem that we encountered in that model they predicted? Because obviously, I'm sure they didn't take that into consideration. Is it true?
You mean in the, let me just find the example, in the example of the electronic tongue?
Yeah.
Yeah.
Exactly.
Yes, I think it's not I'm sure they didn't take limit of detection into account, but I actually don't think it's the limit. Yeah, I mean, yeah, actually, maybe you're right. It's actually completely obscure. There's the bitterness from these different chemicals come for different reasons. There is no signal in these. They use these unselective electrodes, and there's no way they can measure different sort of receptor, different chemical entities that affect bitterness. I mean, the whole thing is nonsense. So in that sense, you're right. There is no limit of detection. I mean, they're way beyond limit of detection. They're basically random numbers, but they could have taken any random numbers and they would still have gotten the same graph, because they have 7 chemicals and 7 variables. I can always, if you plug in random numbers in a 7x7 matrix, you can make it fit whatever you want. So as long as you don't validate, it's gonna be fine.
Okay.
Talk to him.
Okay, Professor, this was my question, because I work with electronic tongue as well, and the next work is gonna be with the same, estimating the bitterness in correlation to the human panels.
Yes.
So I was wondering how to proceed on building the models, because I think I worked with T samples.
Yeah.
I think I didn't know why the model was scattered, the prediction model. I understood maybe there is an error with the reference error.
Yeah.
So
You definitely have to be extremely careful with validation. Now, I don't know what kind of electronic tongue you're working with. Some of them are extremely bad with respect to drift and with respect to analytical results. So I would build this up very slowly, like taking different concentrations of each chemical and build a standard series and see if that works. And then just see if you can actually see the chemicals, and then really focus on validation, making new samples completely, completely new samples and predict those. So I don't think there's a problem as such. If you're a good data analyst, you would immediately see if the model is working or not. I think the guys here had no idea what they were doing. They were not used to building multivariate models. So so I don't think you risk running into any problems, because if it's not working, you're going to see that from your validation of your model. But they simply didn't validate their model.
okay, sure. Thank you so much, Professor.
Oh, thank you.
Okay, thank you. There are more questions there.
Good.
in the chat or here. You have one? Come here. My students here are very active today.
That's good. I like that.
That's good.
Hello, Rasmus. How are you?
I'm good, thanks. How are you?
That was a simple question.
Could
Yeah.
you explain again when to use and when not to use DOE?
Yes. Okay. So if you are trying to model if persons are normal, then you would build a PCA model of 2,000 normal persons. You would not. That's a stupid example. Okay. Let me go back to the process monitoring, because that's where it really makes sense. If I'm trying to model a process, and a process could be a production of cheese, it could be a chat room where I'm trying to monitor if there's weird guys in the chat room. Could be many things. Could be internet activity to monitor if there's an attack of something. Then I want to monitor what is normal. I don't want to go to the extremes. I don't want to have very tall samples and very small samples. I just want to have normal samples, because I'm trying to build a model of what is normal. And for that, I really don't want to use design. So let me go to another extreme, which is actually where design of experiment is crucial. Imagine I'm a pharmaceutical company and I'm doing a clinical phase 3 experiment. There, you really have to, you really have to do a experimental design to make sure that you have really proven that this compound is effective on all different conditions that you can envision. And so a design of experiment is a way to make sure that you get all combinations of all variables. And that's essential if you're doing clinical phase 3. And that's actually the only, that's one of the prime examples where it's crucial that you use design of experiments. Now, if you're building a PLS model to predict protein in milk samples, then it's nice to use design of experiments to make sure that you have both from goats and cows and winter and summer, and you have from humid days and dry days, etc. You use that to make sure that you span all the types of variations that you can envision. And that helps you span the variation to build a model that can predict, under many circumstances. But in this process monitoring case, you're not interested in that. You're just interested, you're basically trying to detect, are you boring? And boring means normal and like all the rest of us. So are you 175 and normal weight and normal blah, blah, blah. And the model you want to build for that is a model full of normal people. You don't want extremes. You don't want some basketball players and some very small persons. You just want really normal people. So you don't want to design and go to the extremes. Does it make sense?
Yes. Yes,
Okay.
thanks.
Okay.
Yeah. More questions there in the chat or here in the audience? No?
One.
Okay, another one.
Very good.
You were explaining the difference between the reference error and the model error. How do I get the information from the reference error? Can I do it on the same experiment, or do I have to do another experiment?
That's a good point. If you buy your references at Eurofins, then when you buy it, they will have a number written, you buy the protein and it's plus minus blah, blah, blah. That actually doesn't work. That's a number they figured out 12 years ago when they implemented the method. And they took 5 samples and they were very careful. What you should do, because you don't want the optimistic, you don't want the pessimistic, you want the realistic measure. What is the actual uncertainty? And you don't want to blame Eurofins, you just want to know. So what you should do is that you should generate samples that you send to them without telling them. Well, now I'm saying Eurofins, but we take that as a concept. So you have to send samples, and you should not tell them that these are replicates, because they shouldn't be treated in any special way. And preferably, you should include sampling variation. That's the hidden, the least part of your error is pushing the button on the instrument. The huge error actually comes from sampling, right? you went out half an hour later because you were a little bit late, and then actually the process has changed. So if you can include the sampling error as well, you really want to put that into the reference error to really understand your PLS model's value. So you have to generate these numbers sort of by remeasuring replicates somehow, and preferably, so if you're a chemist, preferably you want reproducibility, not repeatability.
There is another question here in the chat. To select appropriate wavelength ranges in a spectroscopy, what is the basis for relevant wavelengths?
That's a good question. We can teach a 3-day course on that. That belongs in the subject of variable selection. And I didn't really talk about that here much. But there are tools available that can help guide you. So there are automatic tools that will try to find a set of wavelengths that will improve your predictions. Sometimes you can use your chemical insight. You have to be a little bit careful because of this fact that the model sometimes corrects for something that you didn't know about. But it's perfectly fine to be inspired by your insight. That's a very useful thing to do. But there's a whole set of tools that you can find for automatically finding out what are the useful parts of my data. So there are tools for investigating this. And it's not like a one-button solution. It's more like a set of tools that you can take inspiration from. It's not a real answer, but that's approximately what it is.
Okay, so if there are no more questions, I just have to thank you, Rasmus, again for this beautiful talk.
Sorry for talking so much. It took longer than I anticipated.
No, but that's fine. We want to hear you. So that was beautiful. I wanted to remind the people there at home that, or in the labs, that if everything is fine with Rasmus, I will load this presentation on YouTube. And also there will be a direct link in the IREA website, if that's fine for you, Rasmus.
I think so. Did I say anything stupid?
Yeah, you can say, no, but you can say stupid things. That's fine.
Okay, good. Okay.
And also, I will send you an email to all the chemometrically speaking gang, announcing that the next speaker, the next speak will be in 1 month time, and it will be ASCA, ANOVA Simultaneous Component Analysis, and the speaker will be Federico Marini. For those who don't really know what ASCA means, I will send a couple of papers and I can tell you there is a very nice way of calculating relevant factors in your multi-way data. So that's all. Rasmus, again, tak, and see you very soon.
Yes, I look forward to that. Have a nice day, all of you.
Okay, bye-bye.
Bye.
Bye.